name is Azadeh Shariati. I'm a research fellow from University College London. Welcome to our presentation on dynamic modeling and visco-elastic parameter identification of a fibre-reinforced soft fluidic elastomer manipulator. This is a research done in University College London. A soft robot is a mechanical system that is flexible and compliant and not as hard as rigid systems. Rigid robots, when they hit you, they hurt. Fluidic elastomer robots, which are the subject of this study, are in the class of soft robotics. Other soft robots include tendon-driven and fluidic-driven bellow-actuated. Continuum robotic manipulators have been inspired by octopus arms, elephant trunks, eels, and snakes able to bend and navigate around obstacles. Continuum robots can be soft or not soft. Studies on modeling of continuum robots have mainly focused on kinematics and dynamics of tendon-driven robots, and research on dynamic modeling and real-time control of reinforced soft fluidic elastomer robots are limited. Soft robotics has become an important research topic aiming at a wide range of applications. Soft robots can be very helpful with surgeons, especially in minimally invasive surgery, because the instruments need to enter the body from a very small hole and interact with very delicate organs in uncertain environments, and this must be done safely. The contribution of this paper lies in the system identification for a soft robotic dynamical model that describes spatial and planar movements. In particular, we introduce longitudinal damping and stiffness, planar bending damping and stiffness, spatial bending damping and stiffness. These are visco-elastic forces resulting from the response of the soft material when deformed through fluidic actuation. The paper includes fabrication process of the modified stiff flap manipulator, visco-elastic parameter identification, kinematic and dynamic modeling, and model validation. The soft fluidic elastomer robot used in this study is a modified version of the stiff flap robot. One of the most important design elements of stiff flap lies in the fabrication process. In the fabrication process, each chamber is individually reinforced by a helical thread wrapped around a rod to constrain radial inflation of the chamber when pressurized, and hence to allow only longitudinal expansion. In our new design, we provide an opportunity to change the arrangement of pneumatic input patterns and produce different planar and spatial motions. As all chambers are symmetrically arranged and equally distributed along the central axis, it's possible to apply pneumatic pressures in different ways to achieve planar and spatial motion as illustrated in figures. In all stiff flap, which are highlighted, tubes are connected 2 by 2, so some specific actuation arrangement is not possible. For the experimental setup, we have used pressurized air provided by a compressor. 3 pressure regulators are used to pressurize a single or dual or triple chambers of the manipulator. The pressure regulators receive a control command from a PC via a data acquisition card, and the tip position of the manipulator is recorded by an NDI Aurora electromagnetic sensor. Here you can observe the response of the robot without applying any force and just by applying an initial bending angle and an initial elongation. It's obvious that the robot has elastic characteristics and that the oscillation is damped, so this robot has viscoelastic characteristics in elongation and in bending. Assume that in figure A, one chamber is actuated, so we can model the system with a set of springs and dampers. We can accept that there is an equivalent spring damper on the right-hand side and there is an equivalent spring damper on the left-hand side. The spring coefficient on the right-hand side is bigger than the spring coefficient on the left-hand side, since with the same length, the area on the right-hand side is bigger. As a result, the left-hand side elongates more than the right-hand side, which results in bending. These two sets of longitudinal spring damper could be simplified with a set of longitudinal spring damper and planar bending spring damper. By similar reasoning, if we apply three different forces and produce spatial movement, a spatial bending spring and a spatial bending damper can be added to the model. Here, we have identified longitudinal and planar bending, stiffness and damping ratio associated with this specific class of soft fluidic elastomer robot, and later on we have used them in the dynamic model. To measure the longitudinal stiffness, three symmetrical chambers are actuated simultaneously with the same pressure, resulting in elongation. This experiment was repeated and then pressure data is plotted versus tip displacements. Using a Hawkian stiffness assumption, the longitudinal stiffness KL was approximated. To determine the longitudinal damping coefficient, an initial longitudinal displacement is applied to the robot and the transient response of the system is investigated. As you can observe, the response is overdamped, so an exponential curve is fitted to the result to assess the damping ratio. Then the longitudinal damping coefficient BL is approximated. To identify the bending stiffness, an initial longitudinal displacement is applied to the robot. Since the Aurora sensor data is position of the end effector, bending angle theta and arc curvature can be obtained by these equations. Using the bending moment versus theta, bending stiffness is then identified. You can observe that bending stiffness is a nonlinear function of theta. For identifying the bending damping coefficient, an initial planar bending angle is applied to the manipulator and the corresponding time response is measured. As the system is underdamped, the logarithmic decrement delta theta is obtained from the time response of the robot. Then the damping ratio of the corresponding bending is obtained and the damping coefficient is approximated. Extensive work has been conducted on kinematic and dynamic modeling of continuum robotic manipulators, such as tendon-driven and bellow-actuated robots. Investigated both model-free and model-based dynamics for soft fluidic elastomer robots has been less explored. In this research, we derived dynamical equation for the general spatial movement of the fluidic elastomer robots. A well-known and widely used method for kinematic modeling of continuum robots is the piecewise constant curvature approach, and this is applied here. The kinematic calculations are in the configuration space, returning L, theta, and phi. The variables theta and phi are the planar and spatial bending angles, and variable L is the length of the manipulator due to the applied pressure. Constant curvature assumption can cause singularities in the kinematic model and result in dynamics. The Taylor expansion method is used here to avoid singularities when theta equal to 0. The first 5 terms of the Taylor expansion is used in this paper. The dynamic equations are obtained using the Lagrange approach. Dynamic equations for spatial and planar motion were obtained as follows. The main difference is in generalized force because the position of the applied force in spatial motion is different from planar motion. Forces and moments in dynamic equations have two components. One is generalized force and the other one is visco-elastic force. The generalized force is obtained by its usual equation as follows, where FB is utilized to identify the forces produced by the air pressure P in each chamber. The second component of force Qi has resulted from the viscoelastic property of the material, which is shown by F viscoelastic longitudinal, M viscoelastic planar bending, and M viscoelastic spatial bending. We have identified the corresponding viscoelastic coefficients previously. Now, all the parameters in the proposed dynamic model have been identified. To validate the proposed dynamic model, real-time responses of the system to elongation and bending is investigated and compared with the simulation results incorporating the identified parameters. In these figures, you can observe the results of two sets of experiments. In the first set of experiments, pressure inputs were applied to chambers 1, 3, and 5 simultaneously, and pure elongation was produced, and the corresponding time responses are plotted for both the physical experiments and simulation. In the second set of experiments, pressure inputs were applied to chambers 1, 2, and 3 simultaneously, which produced bending. The pressure inputs applied to the simulated model were the same as the actual step input applied to the physical robot. The result validates the accuracy of the identified bending and longitudinal viscoelastic parameters. In conclusion, in this paper, we have obtained dynamic models for the spatial and planar movement of soft fluidic elastomers. Then, we identified parameters related to the viscoelastic behavior of the robot during elongation and planar bending motion experimentally, and incorporated the identified parameters into our model. Next, we validated the modified dynamic model in experiments, comparing the time responses of the physical robot with the corresponding outputs of the simulation model. The dynamic model obtained in this paper can be used for designing model-based dynamic controllers in future. Thank you.